our s squared term is going to be, we have a k1s squared. Oops. Oh, sorry. Yeah. Okay. Yeah. So we have a k2s squared. We have a k1s squared, but we know k1 is 3/5. So it's going to be plus 3/5. Then for our s term, we're going to have we have a k3s. And then our s term over here is going to be, we have a 2k1s. But remember, again, k1 is 3/5. So that's going to be 6/5. Okay. And then it's going to be plus, we have a k1 times 5. k1 is 3/5, so k1 times 5 is going to equal 3. And in this case, we now know that, so for this to be true, this expression has to be true for all values of s. So for this to be true for all values of s, so we got 3 on both sides, those cancel, we're left with 0. So in order for this expression to be 0 for all possible values of s, these coefficients here must be 0 for all values of s, right? These must be, the only way to make this true is if these are both 0. So what does it take for these to be both 0? K2 has to equal negative 3/5, and K3 has to equal negative 6/5. Okay. So now we have our solution. If we go back to this form, we have our assumed solution up here. We can just fill these coefficients in. So we have K1 is equal to 3/5. And we have K2 is equal to negative 3/5. And we have K3 is equal to negative 6/5. Okay, and now I'm going to erase the rest of this. Okay. So we have our expression now. So we have done our partial fraction expansion. The question now is, how do we do an inverse Laplace transform of this? This one's fairly easy. We know how to do an inverse Laplace transform of this term. This one's a little bit tougher. So the way we find the inverse Laplace transform of this is we remember our sinusoid relationship for Laplace transforms. And we know that the Laplace transform of a e to the negative at cosine omega t plus b e to the negative at sine omega t equals, that all equals a s plus a plus b omega over s plus a squared plus omega squared. Okay. So what do we have to do then? We have to, in order to find these sinusoidal terms for our inverse Laplace transform, we have to get this expression here into a form that looks like this to find this solution. So we essentially have to rewrite this guy to look like this. And to do that, we're going to start in the denominator. So we are going to so we're basically going to have to complete the square here to get something in this expression here. So we're going to complete the square on s squared plus 2s. So why don't, just as a refresher, why don't you pause the video right here and try to sort of complete the square, try to get this denominator into a form that looks like this. So pause the video and then try to do it on your own, and then when you unpause it, we'll come back and do this. So pause. All right, welcome back. So now what we're going to do is we are going to complete the square here. So to do that, we are going to say Well, first thing we're going to do is I'm just going to clean this guy up a little bit. I'm going to clean up. I don't like these fractions in the numerator, so just as sort of a matter of sort of getting this a little bit prettier here, I'm just going to do negative 3/5 times this whole thing, and I'm going to do s plus 2 over s squared plus 2s plus 5. Okay, so same thing. I'm just going to move this negative 3/5 off to the side here and just make it a little bit cleaner for myself. Okay. So completing the squares, we're going to have b divided by 2 squared. So 2 divided by 2 is 1 squared is 1. So we're going to have to rewrite this denominator as, so that's going to have to be a 1. So we're going to have plus 1. And then we can't just add a plus 1, so we're going to have to do a minus 1 over here as well. So what we're left with is this term right here is going to be s plus 1 squared. And then we're left with a negative 1 plus 5, which will be 4. So we can rewrite this as negative 3/5 s plus 2 divided by s plus 1 squared plus 4. Okay, now we're starting to look a little bit more like this. So now we know our a is going to be 1, and we know that our omega is going to be 2. It's going to be the square root of 4 here. So we got, so we know a is equal to 1, and omega is equal to 2. Okay, so I'm going to go back a little bit. Sorry for the limited board space here. Go back a little bit, and now we got to rewrite the numerator as, so we had an s plus 2 in the numerator. We are going to have to now write that as, so we know we have to have this, so omega is 2. Oops. So hold on, let's just write what we know in the numerator. So we have to have an s plus a, or a is 1. We have to have b times omega, which is 2. And this guy is a here. Okay. So what do we know? So in our numerator we had an s plus 2 here. So we know, because we only have a single s in the numerator, we're going to have a single s here, which means a has to be 1. So a's got to be 1. We'll just leave it like that. So we've got that s plus 1 here. But this is actually 2. So we have s plus 1. So what's left in our numerator is 1, which means b times 2 has to be equal to 1, which means b has to be 1/2. So this guy has to be 1/2. And we'll just leave that in there. So, and this is all divided by s plus 1 squared plus 2 squared. Okay. So now we have this equation in the form we had over here, where we have an a term, we have a b term, we have a big A, a little a, and we have our omega. So now we can go back and plug these values into that sinusoidal equation that I had written previously that I'm not going to rewrite because, come on. But why don't you try to do that? So why don't you rewind the video or just use the equation and try to plug these values back into that equation and get the inverse Laplace transform for the function, and then I will just write it out through the magic of television. All right, so pause the video and try to write that out on your own. All right, welcome back. So hopefully you were able to write the inverse Laplace transform of this. I'm going to write it in magic of television. You can also look at your textbook.